All right, so what I wanted to show you today was I wanted to show you about how to defend against memory safety vulnerabilities. Okay? So last week we looked at how these kinds of vulnerabilities work. How do they, how do people exploit your memory safety vulnerability? And memory safety vulnerabilities are one of the most common techniques for hacking into people's computers. So the malware that's spreading, people who are doing remote zero-day attacks against computers, many of those are exploiting memory safety vulnerabilities in some code that your computer is running. So I wanted to talk to you the first half of today's lecture about how we can defend against them. The reason we study attacks, how attacks work, is so we can understand what the bad guys are going to do, and then we can think about how to make those attacks less effective, how to protect ourselves against those attacks. Okay? So I'm going to just kind of show you a survey of some techniques that have been put in place to defend against memory safety vulnerabilities. Okay. We kind of touched a little bit, actually, last lecture. We kind of just hinted at some potential defenses. Does anyone have any in mind about how you might defend against memory safety vulnerabilities? Yeah? Don't use gets. Yeah, don't use unsafe library functions. Yep. We'll come to that today. Yep. Be careful with integers. And why should I be careful with integers?
Because it might be negative, and it might be overflow.
So be careful about overflow, because often I use integers to represent lengths of buffers, and so be careful when doing calculations of things that are lengths or counts. Anything else? What choices do I have as a software developer? Does my choice of operating system make a big difference? If I switch from building my application for Windows to building it for Mac, does that significantly change the risk of memory safety exploits? I see some yes, I see some no. Tell me a reason why someone might say yes. Yeah?
Because one operating system might use 64 bits instead of 32.
Okay. You want to tell me a reason why someone might say no? Yeah?
Because the memory that you're trying to corrupt as the attacker is already memory granted access by the program. So like, I don't know how the OS kind of already gets it from there.
Yeah, so if I already have some bug in my code that can cause memory to be accessed the wrong way, sort of, it's already too late before the OS can even get involved. Did you want to suggest something? The instruction sets are pretty similar. So I don't think the operating system's going to make that big a difference unless the operating system comes with certain defenses. What about the language that I use? The choice of my programming language? Does a software developer make a significant difference to the risk of memory safety exploits? Yeah?
Maybe using higher-level programming languages where you don't have that much control over how the memory is exactly being stored is better. Especially if you're like a naive or an amateur programmer, then like using some low-level systems programming language and like C, where you can like deal with these situations but you don't necessarily have the proficiency to deal with it.
Yeah, I know it's really hard to hear with this fan going. Sorry, so let me repeat back to the gist of what you just said, which was maybe higher level programming languages might be safer, especially for inexperienced programmers, than low level languages like C, where you have to deal with a lot of details of memory. What do you think about that? Do you think that's true, and why? If so, why? You don't have to have a definite answer. You can just like share maybe a half-baked thought. Yeah?
Like in Python, you don't really have to worry about if something's stored as like unsigned versus like a signed integer.
In Python, I don't have to worry about like the signed versus unsigned stuff because Integers in Python don't overflow. They're unlimited in size. And in C, there's trying to like optimize, you know, so you have to, so they're fixed length. But in Python, the focus is on correctness and they're unlimited length. Okay, so that's one class of vulnerabilities I don't have to worry about in Python. Yeah. Oh, that's interesting. Python I often use more as like a glue code to glue together some libraries that someone else wrote. And if there is a vulnerability in those libraries, hopefully someone will notice it and it'll get fixed. Rather than writing the code myself when I can introduce bugs. Uh-huh. Yeah?
Like higher level languages are generally, they were created after C and like lower level languages. So maybe the creators are kind of thinking about vulnerabilities that were happening in older languages that are addressed.
Maybe the language designers were thinking about these risks. The more recent languages would be thinking about these risks compared to older languages. Can I write, let's do a check. Can I write a buffer overrun code in C code? Sorry, a buffer overrun bug. Can I write a buffer overrun bug if I'm writing C code? Is that possible? Yeah, we just saw examples. Could I write a buffer overrun bug if I'm writing Python code? Maybe? Probably? No? Feels a little harder because like in Python I'm working with lists. If I have a list with 3 elements and I try to access the 6th element of that list, what happens? Does it go reading or writing in memory after the end of that list? No, it throws an exception, right? So Python has automatic bounce checking, whereas C doesn't have automatic bounce checking. What about in Java? Can I write a buffer overrun? No, you can't because Java always does bounce checking on all array accesses. What about assembly language? Could I write a buffer overrun bug if I was writing an assembly language? Yeah, totally. Okay, so a lot of newer languages, a lot of higher level languages have built into them automatic bounce checking. And in fact, they're designed so that they will be memory safe, meaning that it's impossible to even write a memory safety bug, to even write a buffer overrun bug, because they'll do all the checks necessary and throw an exception for you. Whereas in C, you, the developer, have to do the checks yourself. The language isn't going to help you. The compiler isn't going to help you. Okay, so that's definitely one defense, is choosing a memory-safe programming language. So I'm going to show you some other defenses. Yeah?
I guess my question is that if the only benefit to C is like a higher, like faster execution time, whereas for other higher level languages it's much more safer and stuff. So why is C still used?
Why is C still in use?
Like other than teaching.
It's so dangerous.
Yeah.
Other than performance. Okay, one thing is speed.
Yeah, other than speed. Like, is it used? I'm not really
Is it in use?
I'm not sure.
What do y'all think?
There's a bunch of legacy code that is impractical to rewrite other methods.
Yeah. So there's two reasons C is in use. C is somewhat in use still, and there's 2 primary reasons. One is for certain applications where you really need the low-level controller, you really need super high performance, like operating systems, typically written in C. Critical parts of games, often written in C or C++, so you can like optimize and get the fastest possible frames per second.
Yeah.
The other reason is there's a lot of code that was written in C a decade ago, 2 decades ago. We call that legacy code. It's existing, where it mostly works, or it works, so I'm going to keep using it. Maybe we want to add some new features. It's a lot cheaper to like add a few more features by adding on to this existing thing than to rewrite the whole thing in Java or Go or Rust or Python or whatever your favorite modern language is. Yeah, so there are two primary reasons why C and C++ is still used a lot. Yeah. But many security people would love to see pretty much the end of C, because that would be mostly the end of this class of vulnerabilities, so we don't have to worry about it anymore. This has been plaguing us for like 3 decades. It would be awesome if we didn't have any more decades of memory safety problems. Okay. Unfortunately, it's not that easy because of the legacy code problem. So it happens, the change happens slowly. Okay. So why are there vulnerabilities? We've kind of been talking about that. One of the key reasons is because software developers are humans, and we all make mistakes. And if the language or the programming environment of the libraries make it possible or easy to make mistakes, and the consequence of those mistakes is buffer overrun vulnerability, then that's really bad. Then we have memory safety problems. So some of the approaches are to use safer programming languages. We've been talking about that. Another way is to teach developers how to write code that doesn't have these problems. Hence why I'm teaching you about this stuff. So that when you write code, you will be thinking about this and take care. Another way is to use tools to help us go find instances of these vulnerabilities. And another way is to modify the compiler or the runtime system or the operating system to make it harder to exploit these bugs. So that if the bugs do exist, then it's more work for attackers. So we've already talked about memory safe languages like Java or Python or Go. Most modern languages now are designed to be memory safe by design, so they just you can't even express a memory safety vulnerability. The compiler automatically does all the checks necessary to make sure it won't happen. Those are great. These are great. Why not? Performance and legacy. But you still, I think in a lot of settings, memory safe languages are reasonable, are often a viable alternative. In a lot of applications, most of the code is actually not that performance critical, and the performance impact from using a memory safe language is often fairly insignificant. There are some exceptions, but often. In places where we really need the highest possible performance or we need some low-level control, there's some more recent languages that aim to give low-level control along with compiler-checked memory safety. Rust is probably the prominent one right now. And also, in a lot of applications, there's a small core of the code that is really performance critical. I don't know, the stuff that is, like rendering this scene, doing some graphic operation and rendering it to your screen really fast. And often you can take that really critical code, write it in C, maybe put it in a library, check that code, be careful when you're writing that code, and then all the rest of the code can be in Python or Go or C# or whatever. And so you've limited the risk to only that small performance-sensitive subset of the code. So let's suppose we're writing code in a language that is not memory safe, like C or C++ or assembly language. How do we be careful? How do we make sure that we don't have any of these memory safety vulnerabilities in our code? Learn about what the flaws are and be aware of them. Defensive programming says, before I do any operation on memory, check to make sure that it'll be in bounds. Check that the array index will be at least 0 and less than the size of the array. Even if I think it probably is, do a check just in case, just to be sure. Make it really easy for a code reviewer who's looking at the code locally to see immediately, oh, it's obvious that it's doing all the checks to make sure that all the array accesses are in bounds. Or use libraries that are designed to do all these checks for you. So for like string processing, there's a bunch of older libraries in C that don't do these checks, but then people realized, oh no, we've got the memory buffer overrun problem, and they design new libraries that will do all the length checking for you. So example would be fgetus instead of getus, or strlcopy instead of strcopy. strlcopy takes an extra argument, the length of the buffer that you're copying into, and make sure it won't write past that length. snprintf takes the length of where you're printing and make sure it doesn't print more than there's space available, and so on. Okay, so if you use the right libraries and APIs, then they can do a lot of the work for you to do bounce checking. But of course, this does require the developer to make sure to always use these safer libraries and not the less safe ones. There's a fancy way that you can use to verify your code doesn't have any memory safety vulnerabilities using techniques from program verification. If you want to learn about that, you can take a class on compilers and formal methods and program verification. Basically you write down invariants for each loop for what holds true and what preconditions you can count on to be true at the start of a function and what post conditions that function isn't responsible for ensuring at the end. And you make sure that all those preconditions and invariants are sufficient to ensure that all array accesses are in bounds, for instance. But it's pretty tedious, so I'm not going to try to walk you through that machinery. Another method to help avoid these problems is to use tool support. And people have built tools to like scan your code, look for patterns that are often indicative of potential memory safety bugs, reason about your code and try to identify vulnerabilities, test them at runtime, monitor the execution of your program to check for any kind of runtime execution that looks like it might be an attack or a memory safety vulnerability. So one example is many compilers have compiler flags that you can optionally enable that will add in bounce checking checks to your code. And it slows down your C program. But now the compiler makes sure that all the checks that are necessary are there. And if you have a memory safety bug in your code and someone tries to exploit it, those checks will catch it and like cause the program to crash. Another defense is to monitor the behavior of your code, not looking for the memory corruption, not looking for the access to out-of-bounds memory, not looking for like that memory access that overwrites the return address, but instead looking for using heuristics to detect signs that are like common in shellcode, looking what the shellcode might be doing, looking at the behavior of the program. For instance, if shellcode often downloads a new program and calls execve to run that new program, and your legitimate source code never calls execve, then you could have the operating system monitor your program, and if your program ever calls execve, that's not legitimate, must mean that it's been compromised and someone's running some shellcode. So heuristic methods to try to detect bad things that attackers often do. And this is not a reliable defense, but it might help detect some attacks. Another defense is to try to limit the damage if there is a bug in your code. For instance, if I have some software that I'm not sure I trust, it was written by some third-party developer I've never heard of, they have no reputation, they're a fly-by-night operation, they might have vulnerabilities in there. Should I run that code as administrator on my machine? Probably not, because if its bugs get exploited, then now the attacker gains administrator level access to my machine. Instead, I could run it in a virtual machine that doesn't have access to any of my files, can't make network connections, copy into that virtual machine only the files that program needs, and now if there's a vulnerability in that program that gets exploited, the damage is limited to whatever's inside that virtual machine. So this is like sometimes called like a blast containment. You're trying to like limit the damage, the blast radius if it gets compromised. And there's lots of other techniques. You can use tools to scan your code for bugs. You can use code review. Ask another developer to look over your code and check, help make sure you didn't introduce any of these bugs. One technique that's widely used in industry today is testing. You test your program, and the testing software tries to come up with inputs that will cause the program to write to memory out of bounds. And if your program writes to memory out of bounds, there's a good chance the program will crash. So if the testing software can find any input to your program that makes it crash, you should be worried you might have a memory safety vulnerability. And so then these tools will try running your program on many random inputs, or take a valid input to your program and try tweaking it, modifying it a little bit, and running your program on many variants of that, and see if your program crashes on any of them. That's the kind of thing that can be done automatically, can run for 24 hours in the background. They can try a million different random inputs and see if any of them make your program crash. And just empirically, this is more effective than you might think at finding some memory safety vulnerabilities in programs. So it's widely used in the industry. It's called fuzz testing. I don't know if it's apocryphal. The story that I heard about how this was invented or discovered was that some security academic researcher, like, oh my gosh, 40 years ago, 50 years ago, was working from home and logging into the computer, like the servers at the university, by modem. Because that was how you did it then, was you called up on the phone line with a modem. And there was some line noise or something. I don't know. It was raining or something, and there was a little bit of noise. And it caused some glitch in the data that was being sent, which was they were writing in some file or something like that. And it introduced a little bit of noise into their file, and they ran the program on that file, and the program crashed, and they realized there was a bug in their code that had been revealed because of this random inputs. And they realized, oh, this is a useful technique. I should automate this. One of the challenges in practice is that most software today relies on lots of libraries and components from other sources, potentially hundreds of these. And if any of those has a vulnerability, your software could be affected because your software is using that library. So there's a kind of a management headache of keeping track of all the vulnerabilities in any libraries that you use and making sure to update to the latest versions of those where those vulnerabilities are fixed. Okay, so those are just some of the pragmatics. Let's talk about some of the technical mitigations, technical defenses to make it harder to exploit memory safety vulnerabilities. So these do not eliminate the bug in your code. Instead, they're a fallback. If your code has a bug, what can we kind of do so that the attacker's life is harder? It's harder or maybe impossible for the attacker to exploit the bug and run malicious shellcode. And these are particularly relevant with legacy code. So like imagine you're working on the security team for a company and there's this giant code base that's existing in the company, or this product you just bought. It's this large pile of C code. Who knows? It might have memory safety bugs in it. It's really not feasible to tell. What can you do to protect yourself? You can't rewrite all that code. You need to run the code. What can you do to protect yourself from possible memory safety bugs in that code? And a lot of the techniques I'm going to show you are based on trying to detect exploits and turning them into crashes. So that instead of the attacker causing the program to jump to this malicious shellcode and malicious shellcode getting executed, instead the program just crashes, which is safer. So if we look at the steps of an attack, the way these mitigations work, I'm going to show you multiple mitigations. Each mitigation tries to identify one step in the attacker's workflow and make that part of the attacker's life hard. Try to mess up that stage of the attack. So a typical attack will have 5 stages here. You find a bug, you get shellcode in memory, overwrite the return address with the address of the shellcode, return from the vulnerable function, begin executing malicious shellcode. So to come up with a defense, the basic strategy is we pick one of these, and then we add something to our compiler so that that step will fail, hopefully. And I'm going to focus on mitigations that target steps 2, 3, and 5 above. So I start with one really basic one. It's called non-executable pages. And this targets step 5, where the attacker tries to cause the CPU to start executing malicious shellcode. Typically, remember these exploits, the attacker causes the shellcode to get copied into memory somewhere, maybe on the stack, and then overwrites the return address so the CPU will start executing from that place in memory. Now that's a little weird because your actual program code is living not in the stack, it's living in its own segment, the code segment, a separate region of memory. So it's a little weird to execute code from the stack. Normal programs normally don't do that. So the idea behind this defense is we're going to say, let's prevent that. The benign programs should never need to execute code from the stack. They're only executing code in their separate code segment. So for every page of memory, the processor is going to keep track of a bit that says whether or not it's allowable, it's valid, to execute code that resides at that address on that page of memory. So in this way, we can mark some regions of memory, the code segment, as executable. It's okay to execute code that lives in the code segment. But we can mark other regions of memory as non-executable. Don't execute any code that you might find in these regions of memory. Even if the return address says to go there, don't execute that code. What would be an example of a region of memory shown on the right here that I might want to mark non-executable? Data. Data holds global variables. It would be weird for that to have code in it, so that'd be fine to mark that non-executable. Any others? The heap. The heap usually holds stuff allocated with malloc, data structures, like trees or linked lists or something like that. No code there. Shouldn't be any code living there, so we can mark the heap non-executable. And
The stack.
and the stack. The stack holds data, local variables, and like saved registers and arguments and so on. No code there, so we can mark the stack non-executable. So actually, we can mark all of memory non-executable except for the code segment. The code segment should be marked executable.
So like, is it basically that over time people have sort of designed things with security in mind, which is at the beginning, C was only designed with security in mind? Sorry, I missed that. Okay.
Design with security in mind?
Like C as a language at the very beginning wasn't designed with security in mind. Like that's like the whole lesson is just to design things with security.
Yeah, you could consider this as an instance of designing with security in mind. Yeah, that's reasonable. Like designing the memory layout with security in mind. And especially the permissions on the pages. One of the reasons why it wasn't initially done was early processors didn't have this notion, didn't have a way to mark a page as can execute or can't execute. Every page could be executed. And then, well, then processors started to support this. Yeah. Yes?
I'm not sure if you already said this, so I apologize if you did. How do you mark something as non-executable?
Good. How do you mark a page as non-executable? The answer there is, if you've taken CS162, is you use virtual memory and you use the page tables. So the virtual memory subsystem is responsible for mapping from virtual addresses to physical addresses, and it does that using the help of page tables, which are a data structure that basically store like a hash map or something. It's not really a hash map, or a tree map data structure. The programs, when it deals with addresses, always deals with virtual addresses. The integrated circuit deals with physical address, so the virtual memory subsystem translate virtual addresses to physical addresses. It does that by looking up what page the memory address is in and then finding out where on the chips that corresponds to. That data structure that does that mapping has space for an entry in there that says, here's what operations are allowed on this page. And one of the bits that can be set for a page are, it's okay to execute code from this page, or it's not okay to execute code from this page. So the CPU, when it goes to an address, it looks up that mapping, and it checks whether it's in a page where execution is allowed. And if it's trying to jump to an address in a page where execution is not allowed, the CPU says, call the whole thing off, crash, halt. Okay, so if you know how page tables work, it's another bit in the page table. Other bits that are in the page table, another bit that's in the page table is, can this page be written to? Is it allowed to modify this portion of memory? And if you clear that bit, then the portion of memory gets treated as read-only. So you can mark a page of memory as read-only, you can mark a page of memory as non-executable.
Are you able to like find where those flags are and flip them if you want to still exploit the system?
Can an attacker find where those bits are and flip them? Yeah, good question, good question. The answer is that data structure, the page table, does not live in memory space of the program. It's under the control of the operating system. If the program wants to change that, it has to call the operating system and say, would you please make this change for me? If the operating system is glad to oblige and make any change, you could think maybe the attacker could call the operating system to mark the stack as executable and then execute shellcode there. But for the attacker to do that, they would first have to get this program to call the operating system to mark the stack as executable, which would require executing code to call the operating system, but they can't execute code until they can mark the stack executable, so they kind of can't. And also on systems that will use this, maybe this might be built into the operating systems. The operating system might have an idea of what pages should be writable and what can be executable. Now, there's a big flaw in this description that I gave you just here. It turns out that just marking pages non-executable is not enough. Because there is still one bad thing an attacker could do if they can exploit a buffer overrun vulnerability. They can only execute code from this region. They could try to write their shell code in the code region. And then that would be successful, because this is a region that's executable. So we have to stop that too. And the way we stop that is we say within the code region is non-modifiable, it's not writable. So when your program gets loaded up, the loader stores all the code in here, and then it marks this as not writable anymore, no further changes allowed. And then before it starts the program running. So what that means is that every region of memory is either writable but not executable, like heap and stack, or executable but not writable. There's no region of memory that can both be written by the program and executed by the program, which ensures that the program will only execute code that was already there at the start. So it basically prevents an attacker from executing malicious shellcode. The attacker can copy malicious shellcode into the stack, but they can't execute it. They can't copy malicious shellcode into the code region because it's non-writable.
Is there any way that an attacker could have the operating system believe that this area should be writable instead of executable?
There may be crazy ways to try to get the program. If you can get the program to execute a certain amount of malicious, to make this call to the operating system to change the status of pages, but then you have to get the program to execute that code. Usually that's not feasible. When we see ROP attacks, we'll see a crazy way that you can exploit this. But it's pretty hard. It takes a bunch of work. All right, so this goes by multiple names, non-executable pages. In Windows, it's called DEP. So a lot of people call it DEP. You might see this called DEP. Other questions, or shall I move on? Okay. You were asking, are there any ways to defeat this? There are ways to defeat this. At first glance, they look like they're not that significant, but actually they've turned out to be pretty powerful. One thing that doesn't stop it doesn't stop an attacker from executing whatever code is already in the code segment. Any code that's already in the code segment, the attacker can run. Now you might think, no big deal. No big deal. That's code the program was designed to run, so of course, I mean, what's the harm if that gets run? But it's not quite that simple. One example would be if there's some code in there that not everyone's supposed to be able to run, and it has a check to make sure that you know the administrator password, and then if you know the administrator password, then you can call this function and do this dangerous operation. An attacker who can overwrite, knows of a memory safety vulnerability and can overwrite a return address, can overwrite the return address to point to the code that does that dangerous operation after the check for the password has already been done. And the dangerous thing will be done even if the user doesn't know the password. That still seems kind of minor. But there are more serious attacks. And the more serious attacks are called return to libc and return-oriented programming. And I want to show you these. Return-oriented programming in particular blew my mind when I saw this. Like, oh my gosh, the cleverness of this. So beautiful, even apart from any practical relevance. Incredibly clever. So let me start by telling you about return to libc attacks, which at first, when this non-executable pages defense was deployed, it was like, whew, this looks pretty good. I think we basically solved the problem. And then within a year or two, bad guys started finding ways around it. And they first started using return into libc attacks, and then they started using this fancier version, return-oriented programming that I'll show you next. So return to libc, the idea is to run some code that's already in the code segment. And one, like on Unix with C, one thing that's in the code segment is the standard library, the standard C library. Standard C library includes all sorts of functions that do all sorts of things. One of the functions that's in the standard C library is the system function. And the system function lets you pass a string that contains any Unix command line, and it will run that command line. So, what an attacker could try to do, don't introduce their own malicious shellcode. Instead, get the program to run this system function, but with an argument of some command line that will do something really bad. Like in this example, erase the whole hard drive. But maybe it could be something else, like email your Bitcoin wallet to the attacker. Or like upload your SSH private key to the bad guy's FTP server or something. So let me show you how an attacker could exploit a buffer overrun vulnerability using this return to libc to invoke the system function, even though we have the non-execute pages defense put in place. So here's some example vulnerable code on the left. This vulnerable code calls getS, which can overwrite the name buffer. And there's the assembly code for the vulnerable function. And if we look on the right has a stack diagram. On the stack diagram is 20 bytes for the name buffer. That's a local variable of the vulnerable function. And then above local variables is the save frame pointer, and then the return value, the saved value of the EIP. Okay? So what the exploit is going to do, let me show you, just tell you the exploit, and then show you what happens when you walk you through step by step what happens. The attacker can provide an input up here shown in yellow. 24 A bytes, that's 20 bytes to fill up the name buffer, 4 more to overwrite the save frame pointer, and then overwrite the RIP with the address where this system function is in the standard library. That's in the code segment, so it's in an executable region, so the CPU will be willing to execute code there. When vulnerable returns, it won't go back to main, it'll go to the start of the system function. But the system function is not expecting you to return to it, it's expecting you to call it. So when you call a function, it's expecting kind of the beginnings of a stack frame, right? we're going to need to make sure that memory is set up the way that the system function is expecting, so that when the system function runs, it like does what we want it to do. So what we're going to do as an attacker is we're going to set up a fake stack frame on the stack as though it looked like what would be there if someone was calling the system function legitimately. But it's all fake data that the attacker filled in. And that's what the rest of this bytes of this input are doing, is creating a fake stack frame so that the system function thinks it's being called normally, even though it's actually being returned to. So after we read this input, the name buffer has been filled with junk. The save frame pointer got filled with junk. We don't care. Then the RIP got overwritten with the address of this system function that the attacker is trying to execute. And what does a function expect when it's called? What does it expect to be on the stack when it's called? It expects to have on the stack, the RIP has been saved on the stack, and then right above that, arguments to the function. So the system function, when it's called, is going to treat those B's up there as an RIP. It's going to assume those were an RIP that were pushed by whoever called system. And then it's going to look for the arguments one above those. So right above the B's, we put the address of a string, the address in memory where this shell command that we want to run is placed. And the system command will think that's its first argument and will happily go run, treat that as the shell command to run that shell command, erase the hard drive, boom, damage is done. Yeah?
So it's okay to override the RIP
It's okay to overwrite the RIP with garbage, you said?
Yes, it doesn't check that it's a valid RIP.
In this case, the RIP, okay, we've got to be clear about which RIP we're talking about.
Sorry,
The BBBBB, yeah. That will be treated by the system function as its RIP when the system function is done. So after the system function has already executed the RM command and erased your hard drive, when that's done, then it'll try to return. It'll go treat with the BBBB as the return address. The CPU will try to start executing code at that address. That's a nonsense address that doesn't exist or is non-executable. So the program will crash, but by then your hard drive's already been erased and it's too late. Yeah, so it doesn't do that check in advance. The CPU only checks when you transfer control to that address. Yeah?
How does an attacker find the address of the system and the address of a string like that?
How does the attacker find all these addresses? You have to do this in Project 1, don't you? You're finding all these addresses. How are you doing it in Project 1? You're running in GDB. Why is that possible for you to do? To run in GDB? What did we have to give you to make it possible?
The source code.
Like the source code, or the program itself, that would also work. So what an attacker is going to do is going to try to get a copy of this program that the victim is running, of this vulnerable program, on their own machine and run it in GDB. And they're going to be able to like dump out the stack at this point in execution, like put a breakpoint, stop execution, dump out what's on the stack, figure out the addresses of where stuff on the stack are. This RM minus RF is written on the stack, so we can figure out the address of where that is. Figure out where the address of system is. This stuff is, by default, kind of all deterministic. It might depend on the versions of the libraries you have, but if the victim and the attacker have the same versions of the same programs installed, running the same OS and so on, then they'll end up with the same addresses.
That only works if they're running the same OS.
But it only works if they're running like the exact same version of everything. So in the attacker's life is really easy if they know all the version numbers, because then they can get exactly the right addresses. In practice, sometimes you can get exactly the right addresses. Sometimes you're not sure exactly which version is being used. And so then in practice, attackers do some extra stuff to try to make their exploit work, even if they got they're off by a little bit. Depending on the version number, the address might vary a little bit. So there's all sorts of techniques that bad guys have developed to try to make these exploits more robust if their addresses are all wrong by a little bit. Like, for instance, we talked about no-op sled with shellcode. That's an example of, for shellcode, trying to be more robust if you got the address a little bit wrong. Here, if we got the address of rm minus rf a little bit wrong, what could we do? Well, how could we modify that string, the rm minus rf, so that this would be more, this exploit would work more reliably even if our address was a little bit off? Yeah?
No ops?
No ops. What are no ops for Unix command line? Yeah?
It's just a new line.
Like a bunch of new lines? Start with like 100 new lines, and then rm minus rf, and try to pick an address that I think will be about in the middle of those new lines? But if I'm a little bit high or a little bit low, no problem. So there's all sorts of sophisticated techniques, and that's like just one example of one that attackers can use to try to make their exploits more robust. So you might be thinking, holy cow, I can see how this would be exploitable in theory, but how do these attacks ever work in practice? What I'm telling you is the core of the exploit, and then I'm just asking for your trust that it's ridiculous how reliable attackers have managed to make these exploits, even without much knowledge of exactly the version number on the victim's machine, by doing various clever tricks. And the clever tricks, they're not really worth spending your time learning. I'm sure they'll change in 5 years. But the main point is, like, they exist. So we can't rely on, oh, maybe the attacker doesn't know what version number I'm running. It's not a safe defense against these attacks. Okay, so I could walk through executing. We could like execute each individual line of assembly code and see what it does if we've set up the stack like this. And what you'll see is what happens is this executes through the vulnerable function, and then when it returns, it starts executing code at the system function. And the system function expects its first argument to be 4 bytes above the initial ESP, and so it will use that as its argument. So this return into libc attack allows the attacker to pick any one existing function in the code segment, like in the standard C library, and call that with any arguments the attacker wants, without having to modify any executable page or execute any non-executable page, like without having to put in any malicious shellcode. And often programs will have enough stuff in the libraries that the attacker can do really damaging things. Like if you include the standard C library, you've got the system function in there, and that's enough to do return into libc, and the attacker now can execute any command, and you're a host. The attacker has full control of the program and of your account and all your files and all that. So this is really devastating. This non-executable pages stuff looked awesome. And then attackers found this return into libc exploit, and oh crap, we're kind of back where we started, right? Like, the attackers win, and they can defeat this defense. And they actually got really clever. They got really sophisticated. The first idea was this return into libc. Run any one function that exists in the code segment. And so people started thinking, maybe I don't need the full standard C library. Maybe I can only include in the code segment the functions that are actually called by this program. Maybe I can remove system. Maybe I can remove some of the most dangerous functions so that just calling one function is not that harmful. And then attackers found this attack technique called ROP, which just destroyed non-executable pages as a defense. And what ROP does is it's like a generalization of return into libc, where the attacker can do return into libc, but after they finish running one function, then they can run another and another and another and another. So they're not limited to just calling one function. They can call any number of them, chain any number of them in sequence. So if we look back to this return into libc exploit, where the attacker got the system function to execute and then when it returned, the program crashed. Suppose that the attacker wanted to call one more function after system returns. After system returns, the attacker wants to call I don't know, some other function. I can't even think of an example of some other function. A reboot function. How could you modify this exploit? I'm giving you a chance to invent ROP attacks yourself. How could you modify this exploit so that when system finishes and returns, now the reboot function gets called, assuming the reboot function is somewhere in the code segment? Oh, maybe this is a good chance. Talk to your neighbor. See if you can come up with any ideas for how after system returns, the attacker could arrange that the reboot function gets called next. Talk to your neighbor.
So maybe the RIP system could be the other I saw that.
All right, let's see how you're doing. How many of you together came up with what you think might be a possible solution? Ooh, I really stumped you. Okay. Someone who came up with a solution, why don't you give us a hint? A hint for something that would help someone else find a solution. Do you have a hint?
I was just going to say, I'm not sure if this is right, but maybe after returning from system, like the RIP could contain the address of the second function. I don't know if that's not.
An RIP. Look at the RIP. Would you recommend we look at the RIP for vulnerable or the RIP for system?
RIP for system, because we're going to execute system, and then the stack frame for system is going to be over. So.
Okay. Someone else help me out. How could the RIP for system help us achieve our goal? Yeah?
You could change the RIP of the system to the next thing that you want to call.
Why Why would that help? I'm worried I've lost 95% of you. How are you all doing? Are you, have I totally lost you all? It's a hot, hot day. Are you like, this is so obvious and I just don't feel like saying anything? Lost. Yes, lost. Thank you. Thanks for telling me. Okay, maybe I'll just tell you the solution then, and we can work through why this works. The solution is, instead of BBBBB, we're going to put something else in there. We're going to put the address of the reboot function. Why is that going to work? When the system function starts running, it's expecting that it's been called by someone who set up the stack. And when someone calls you, the way they're supposed to set up the stack is they put an RIP on the stack, and right above that they put your arguments. So the system function is written under the assumption that this calling convention has been followed. That on the stack, at the very, like right on this, where the ESP is pointing is the RIP, and one above that is the argument. So when the system function is done, its code will return. How does it know where to return to? It's the RIP on the stack. Where was that stored? It's right where the ESP was pointing when system got entered. So if instead of BBBBB we put the address of the reboot function, by the time system gets to its return instruction, ESP is going to be pointing back at the BBB, at the reboot. That's where the system function is going to look for its RIP. And it's going to transfer control, start executing at the address found in its RIP. We overwrite system's RIP with, in this case, BBB, or if we're smarter, with the address of reboot. Yeah?
If we wanted to pass more arguments into the second function, how would we do that?
Ah. Arguments are a problem. Let's assume we don't want to pass any arguments to the second function. Yeah. If you want to pass arguments to the first function and the second function, I think you're hosed. I don't think you can do that. I don't know how to do it anyway. Let me try and explain it another way. And then I'll check and see if you're getting it. I know this is complicated. I'm sorry. It's not the most important thing in this class. But it might be maybe one of the most beautiful things that I show you today. So the idea of ROP is we're going to do what I just said, but we can do not just two functions, but any number of them. And in ROP, we look for some small functions that we can call that have no arguments. And so that if I can call them one after another, the end effect is malicious. So let me give an example. Suppose that our shell code involves 2 lines of assembly code that I would like to execute. But I can't put the shell code into the code region. I can only use whatever is already there in the code region. And suppose that I, as an attacker, find in the code region these 2 snippets, amongst other stuff. What do these 2 snippets have to do with the shell code on the top that I wanted to run? Is there any relationship you can spot? Yeah?
They're exactly the 2 lines we want to run, just separated from each other.
There's the 2 lines I want to run, but they're kind of like in the midst of other stuff. I want to do a move L1 into EAX, and that is found right down here at 25 bytes after the start of bar. And it's also followed by a return instruction, which is going to turn out to be important. And then I want to do an XOR, and that's found right here, 10 bytes after the start of foo, and it's followed by a return instruction. So in this case, if I could get the program to first, like, call to right here, 25 bytes after the start of bar, and then to call to 10 bytes after the start of foo, the effect would be the same effect as this desired shellcode. So the way we do that is that we, the attacker provides an input that overwrites vulnerable's RIP with the first thing that we want run, the XOR L, which is at foo plus 10, address foo plus 10. So when vulnerable returns, it'll look in its RIP, which is under the ESP, and transfer control there. So we'll start running the code at wherever its RIP was. Which is bar plus 25. Did I say that backwards? Anyway, this right here is the port of the stack that the vulnerable function is interpreting as its RIP. So when vulnerable returns, the CPU will start executing code at this location, meaning this location. So the CPU will execute the move instruction, and then it'll execute a return instruction. What does a return instruction do? Return instruction looks under where the ESP is currently pointing and jumps there. The ESP pointing is currently pointing here. Each time you do a return, it moves the ESP up 4 and jumps to that address. So when vulnerable returns, it jumps to bar plus 25, which executes this code, and the ESP is now pointing up here. Then when bar returns, it jumps to foo plus 10 and moves the ESP up 4 more. So the return address from vulnerable, the ESP is pointing to that RIP. And when you execute the return instruction, it moves the ESP up 4 and starts executing at that address stored on the stack. So now we execute the move instruction. Then we execute the return instruction inside bar. That looks wherever ESP is pointing, treats that as an RIP, moves ESP up 4 bytes, and jumps to the address that was at where ESP was pointing. So that is now going to jump to foo plus 10 and execute the XOR instruction, and then execute the return instruction after foo, at the end of foo, which will now go to whatever was the next address. So we could have more than 2. I just showed 2 here, but this could continue, this chaining could continue onward. And in this example, I assumed that foo and bar are both parts of the existing code. So they're already in the code segment. So they're already marked executable. So the non-executable mitigation doesn't stop this attack at all. This was a silly example because I just caused 2 assembly instructions to be executed. It's not clear why these 2 would be harmful. In practice, attackers have a shellcode that has maybe 100 instructions long. But hopefully you can see how this would generalize if you had some shellcode that was 100 instructions long. What you'd have to look through in the code segment is for each instruction you want executed, a place in the code segment where that instruction appears followed by a return. And empirically, often you can find these things. Notice this didn't have to be at the start of bar. It could be at somewhere in the middle of bar. It turns out it doesn't even have to be aligned with the intended instruction boundaries because x86 instructions are variable length. It could be in the middle of some other instruction. You interpret it starting at that random location, and it gets interpreted as a move followed by a return instruction. So empirically, in code segments for real programs, you can find lots of these gadgets, enough that you can do everything your shellcode wanted. Well, maybe not every instruction in your shellcode, but maybe there's some combination of instructions that will do everything in your shellcode. And when you look through everything that does exist in the code region, each one of those is called a gadget. Empirically, what happens is you might find 50 or 100 or more of those gadgets. Each does a little tiny operation. And usually, here's the cool part, those are enough to be Turing complete. Those form a programming language with some very simple operations you can do. So you can now write a compiler that compiles from your shellcode to those operations. Maybe your 100 instruction shell code turned into 300 of those instructions. So amazingly, this return into libc allows an attacker, typically, to execute any malicious shell code they wanted by chaining it together a whole bunch of these gadgets. So where are we at? Non-executable pages is worthless against a knowledgeable attacker. They had to be really clever to come up with this, but once they know about this, it doesn't actually stop them. Oh. Now let me check in. How are we doing on how this attack works? I want to take just a class poll of like, maybe I'm getting it and lost. Maybe I'm getting it, lost. Okay, okay. Sorry I failed you. Maybe I'm going to take questions now. And if anybody who's lost wants to ask, like, yes, I love it. And then we'll take a break after that. Yeah?
So what if like a line is not followed by the return? Like what if like the move is like not followed by return? Like we can't.
What if that instruction is not followed by return? Then we can't use it. The chain would have to stop there. We'd have no way for it to keep going. So we need it to be followed by a return. So what people actually do is like maybe there's a megabyte of code in the code segment. Return instruction is 1 byte. So you just look at every place starting there and you hope that it's some instruction followed by a return. Because a return is a 1 byte instruction, you look at any location, there's like a 1 in 256 chance it could be interpreted as a return instruction. So about 1 out of the 256 locations in the code segment, if you just were to go back 1 before that, you would have a gadget that you could use. So you often find a lot of gadgets. Yeah?
So do you have to have the assembly in order to use the gadgets in this way, or can you have this work in C as well?
If the attacker has a copy of the program that the victim is running, copy of the program, like maybe the victim's running the Chrome browser and the attacker found a buffer overrun exploit in it, so the attacker downloads their own copy of Chrome. It's the same Chrome software. They can run it in a debugger, have the debugger look at all the bytes in the code segment, disassemble it. For Chrome, it's open source, so they could even get the source code that corresponds to it. For maybe Microsoft Word, they won't have the source code, but they can still get the bytes and they can disassemble, and there are programs that will turn the bytes back into assembly language for you.
So GDB would be able to like, I mean, so yeah, I mean, I guess you always have to complete like, you have the full program. So
Yeah. Yep.
Gadgets don't have to be like one line, right? As long as they're all the lines in order to the return.
They could be multiple. Yeah, it could be a sequence of instructions. Totally. Yeah.
How to not only like execute one line, but multiple lines and hit return.
The gadget could be multiple lines.
Yes, is that possible?
Yes, the gadget could have multiple instructions followed by a return. For instance, if I wanted to do an AND followed by a move, AND 1 into EDX followed by move 1 into EDX, I could start not at bar plus 25, but like bar plus 23 or something.
How about if it includes some local variables? It's like beyond stack.
Yeah. What if the code that my gadget accesses the stack to use some local variables? Maybe it won't be useful. It's that you look at each gadget, see what it does, and see if that's going to be useful to attack. You have to figure out how to piece them together. If it's one instruction, each gadget is only one instruction, it's easier to piece them together. If the gadget is some convoluted piece of code that's reading from the stack and assumes the stack is in a certain layout and so on, you might not be able to use it because the stack might not be in that layout.
So if we have some like local variables that contain some stack, we can use it.
Usually those are not useful gadgets. Yeah. Let's take a break. take a 4-minute stretch break.
Do I have air conditioners too?
I wish. All right, let's reconvene. So where we're at right now is I had all these great hopes. Non-executable pages, a defense against buffer overruns. And then my hopes were dashed. They don't work. There are exploits against non-executable pages. But don't give up yet. I'm going to show you some other mitigations, and we'll get to some that actually do work. So another mitigation that you may have already started to read about for the project is stack canaries. So let me tell you about stack canaries. Stack canary says, oh, let's pick a different step of the attack sequence. We're going to look at the step of the sequence that tries to overwrite the return address with the shellcode, and we're going to try to prevent the attacker from doing that. Or if they do it, we're going to try to detect it and crash the program. And we're called canaries by analogy to this old mining practice, which is kind of grim or gruesome. They would have problems where like poison gas would build up, but they couldn't smell it, and then miners would just like die. They like suffocate from this gas because they didn't realize it was happening. And so they started bringing canaries. And I don't know if you know this, but like canaries and parakeets, they're like super sensitive to the quality of air, more sensitive than we people are. And that's why they brought them down there, so that if the parakeet or the canary passes out, that's an early warning sign that the air quality is not good, and get out, okay? Or worse, I mean, the really grim part is if it dies, right? Then you know to get out. But I guess, so the death of this canary is kind of like the sacrificial thing, right? It gets sacrificed to save the lives of the miners. So that's the idea we're going to use here, is we're going to have this sacrificial data in memory that might get overwritten to save the life of the RIP. If the canary dies, the miners will leave the coal mine. If the stack canary gets overwritten, the program will evacuate, crash, end without using what's in the RIP. Okay? So we're going to add, the idea is we're going to modify the stack layout. The compiler is going to be modified, so it adds an extra 4-byte value to the stack called a canary value, or canary, which is going to be this extra value that should never change. It's written when the function is called. There's nothing in the program that is designed to modify that. And when the program returns, the code is going to check to make sure that it still has the same value. If its value has changed, oh, something terrible has gone wrong. Maybe there's an attack that's overwriting stuff on the stack, cause the program to crash. Do not return. Do not jump to what's in the RIP. Immediately exit. Okay? So the compiler, when the program starts, is going to pick some random value. That's going to be the value that gets put in the canary. The compiler is going to be modified, so on every function call, the start of the function puts this canary on the stack. And then at the end of the function, just before returning, it checks the canary value to see that it matches the correct value and exits if not. And only if it's correct do you execute the return instruction. Okay? So this canary value will be different. One reason we choose it to be a random value. Why do we choose it to be a random value? You tell me. Yeah?
Well, if it's the same over and over again, we can just read it one time and reuse it in every execute.
If it's the same every time, then an attacker can learn what it is, and when the attacker overwrites this canary, they overwrite it with that known value. So by picking a random value when the program starts, the attacker won't be able to predict what the canary value should be. When the attacker, if the attacker overwrites stuff on the stack and they overwrite that canary value, they'll probably overwrite it with something different. And so it'll be detectable that the canary value has changed. And that will be an indicator that the stack has been, some buffer's been overflowed, the stack's getting overwritten. Oh my gosh, something bad is happening. And as a little trick, often we'll make 1 byte of the canary be a 0 byte, a null byte. And the reason for that is in C, most string manipulating functions handle null terminated strings, so they stop copying at the first null byte. So if the attacker wants to preserve the canary value, they have to have a null byte which will stop copying and won't copy past the end of the canary, basically. If they want to continue copying, overwriting after the canary, then they're going to overwrite that null byte with something non-null, and it'll definitely be detected as changed, because what was null is no longer null.
Can you put it as like the second byte, or there's like no point to put it as the second byte, because like why let it even read the first byte of the canary?
It doesn't really matter whether you put it as the first byte or the second byte or the fourth byte.
But if you put it as the fourth byte, can't it read all the canary and then it'll stop, so you'll know that like the last byte is a null byte, and that's
Oh, that's an interesting thought. If there was a one vulnerability that read up a read overflow and another was a write overflow, okay, that's a good reason to put it as the first byte. I'm convinced. Good thing I'm not designing these systems. So here's how it works. The stack layout is modified. It's modified to add this extra 4-byte value in here. The 4-byte value appears right after the SFP, well, below the SFP and above the local variables. And if you remember the way memory addresses work, this is like 0 and this is like FFFs at the top. So increasing memory addresses go upward. So if you do a string operation that writes past the end of a buffer or an array, it will write, and keep writing upwards. So if there is a buffer overrun vulnerability, like in this vulnerable function, that allows an attacker to overwrite past the end of name, the writing will start to overwrite, and it'll overwrite this canary value. And then maybe the attacker keeps going and overwrites SFP and RIP and so on, but the canary value has been overwritten. And you can see here when the vulnerable function returns, the compiler has added some extra checks here to check what's in the canary value to make sure that it matches what was originally there. So if an attacker, if there's some bug and the attacker has overwritten the canary value will have changed. The compiler's inserted code will detect it as changed. It'll jump to canary failed. A canary failed will end the program. So in particular, if the attacker wants to overwrite the RIP, they have to also overwrite the canary. And thus be detected by that code, and therefore the return instruction will never be executed, and so it doesn't matter if the attacker has overwritten the RIP, because the ret instruction won't be executed and the RIP will never be used if it's been overwritten. Okay?
when you compare the canary on the stack to the saved canary, is that saved canary saved in the register? Like where is that saved?
When the compiler inserts code to check the canary, compare the canary to the intended value, where's that correct value stored? If you look at this blue code, the blue code is what the compiler inserts to store the canary and to check the canary. And the crucial instruction, the check happens in this CMP compare instruction, where it's comparing, it read from the stack what was stored in the stack in the canary slot, puts that in register EAX, and then it's comparing EAX to a value stored in memory at a fixed address. So it's a global variable. The correct value is stored in a global variable, not a register. Why not a register? This is like, I don't know, assembly language guru question. Why not a register? The issue, if we wanted to store the correct value of the canary in a register, we'd have to dedicate a register just for that. There aren't that many registers. There's like 8 of them or something. Now I only have 7. My program's probably going to be slower if I have to, like, one register's out of bounds. So that's why instead it's stored in memory instead of in a register, because registers are very limited. Yeah?
So then if you were able to override memory, then you could technically change the canary in the stack. But also
Yeah, good. You're thinking of exactly what I wanted to have you think about was, I wanted to think about, think like an attacker now. This is the defense. Think like an attacker. How would you defeat a system that was protected with stack canaries? Great. And you gave me one suggestion, so you started our discussion off. Your discussion was, your idea was if the attacker can overwrite memory and overwrite that global variable where the correct value is stored, they could overwrite that correct value with a new value that's known to the attacker. How does that help them?
Because then when you do a comparison, you just compare the values that you designed yourself.
Yeah, then the attacker knows what value to write into the stack. So if the attacker can overflow this buffer on the stack and overwrite the canary and overwrite the RIP, and then also modify the global variable, and make sure that the value stored in the global variable matches what they wrote into that canary slot on the stack, then they will bypass this check. The attack will not be detected, and the canary will be defeated. Okay, great. That is a great way to do it. Notice that that requires, what does that require? It has to like overwrite memory twice. And the overwriting the global variable, it's not enough to just write past the end of some string that's stored on the stack. The attacker needs to be able to like write to some discontiguous memory address. So that's more limited. They need a special kind of bug that allows the attacker to write to any address they want, not just consecutively past the end. And maybe they need 2 bugs, or maybe they need 1 bug that's in a loop so they can do it twice. Once to overwrite the stack, once to overwrite the global variable. So absolutely, that's a kind of attack that could be used to bypass stack canaries. And maybe we're okay with that because some bugs will allow an attacker to do that and some bugs won't. So this maybe has some value for some bugs will become harder to exploit, some won't. Yeah?
A question for detail on this. Is stack canary here a global variable, or is it a constant value?
Haha. It's stored in 2 places. One, it's stored on the stack, and also it's stored in a global variable.
Oh, it's stored as a global variable. It's not stored in the code section.
Not in the code section. Yeah. It's stored in the global variable and also on the stack, and then before you return, you check that both those values match. Okay, any other ways as an attacker that you could try to defeat stack canary protection? Any other ideas? Yeah?
Constantly guess it.
Constantly guess it, sure. How many bits do you have to guess? How many bits are there in a stack canary?
Oh, sorry. You said it's a word? Is that 4?
4 bytes. Yeah, 4 bytes. And how many bits is that? 32? So 2 to the 32. So what are the chances of guessing correctly? 1 and 2 to the 32. How many times do I need to try? 2 to the 32? 2 to the 32 is 4 trillion? No, 4 billion, 4 billion. 4 billion. Barely, maybe that's possible. Good. That's actually a really good idea. Actually, because an attacker can optimize that a little further, I said 32 bits, but it's not quite right. Because the first byte is a null byte. So the first byte the attacker can predict is really only 24 bytes that are 24 bits. 24 bits that the attacker has to predict. So 2 to the 24, so that's like 16 million. That might be feasible. That might be just barely feasible for some programs. Try your exploit 16 million times, and there's a decent chance you'll succeed once. If the program crashes and doesn't restart, not helpful. But if there's something on the system that will restart it if it crashes, might be possible. Good attack. Any other attacks? Yeah?
Just save the canary somewhere and rewrite it.
If the attacker can save the canary somewhere and then rewrite it? Yeah. So one way that could happen is if the attacker can find one bug that allows them to read memory out of bounds and like print it out. And then another bug allows them to write memory out of bounds and to like, so they'll use the first one to read what's in the canary and then the second one to overwrite. Maybe when they're overwrite now the canary with the correct value, now that they know what the correct value is. Yeah, that's a valid attack. You'll notice that to make that work, often that requires 2 vulnerabilities in the program. You have to know of one that allows reading and one that allows writing. So it makes the attacker work harder to find 2 vulnerabilities. If the attacker only can find 1 vulnerability, they can't mount that attack. So maybe you could argue the stat canary has some value in like making it more expensive for attackers. Even though it's not perfect, maybe it can be defeated. And this first type of vulnerability where the attacker reads some part of memory, that's called an information disclosure vulnerability. Yeah?
Is there a way to do like 2 different writes? Like say, to go around the canary?
Yeah, go around it. Yeah. Yeah.
Like it was like starting at one address, write some amount.
Yeah. Yeah, it's like I want to overwrite. There's the canary. I don't want to overwrite that. Just like jump over it and then overwrite some more. Yeah? If I could like overwrite non-contiguously. Yeah, totally. So there are some memory safety bugs will just keep writing sequentially past the end of the buffer. That's not going to help. But there's some memory safety bugs that will let the attacker write to any address the attacker wants, any value they want there. And then that would be the kind of thing that would allow bypassing the stack canary, because the attacker could say, I want to write to the address where the RIP is stored, and the value I want to write is my shellcode address. And that would completely defeat the canary. Do you know of any vulnerabilities? Have you seen any kind of memory safety vulnerabilities in this class that have that property of like attacker can write to any address they want, any value they want, that's non-contiguous? Yeah? Overwriting a pointer, which later is used. Yeah. Any others? Yeah? Format string vulnerabilities allow the attacker to write to any address. So they're very severe because they allow bypassing stack canaries. Yeah, I love the attacks you've come up with. I think you came up with all the ones that I know of or that I thought of. Attacker can try to leak the value of the canary using information disclosure. They can bypass the canary using your idea, or they can guess the value of the canary by brute force. Okay, so stack canaries are definitely not a full 100% defense, but they may be a partial mitigation that for some vulnerabilities makes them harder or impossible to exploit, and others is not enough. Or maybe increases the cost for attackers. They have to find multiple vulnerabilities before they can hack your system. Okay. Another defense, I'm going to skip over this defense. There's another defense, which is you can do something like stack canaries, but instead of putting this canary value in the stack, you put in some of the bits of the pointer that are not used. And then the CPU checks that those values are not changed, and this will detect any overwriting of pointers. And code addresses are a pointer. So you can do this with all addresses, like return instructions, return RIP values too. So ARM, the ARM processor, including like Mac and all phones, support pointer authentication. Okay, you can read about that in the slides if you want. One more mitigation that's very widely used I want to tell you about is address space layout randomization, ASLR. That's kind of a mouthful. But it gets at some of the questions you were asking very like insightfully earlier about like how does the attacker know what the addresses to put in here are? What if, what if those addresses are not right? And I said that those addresses are static and deterministic. If you and I are running the same software, the same versions, we get the same addresses. No reason why it has to be that way. So some security people came up with the idea of saying, let's change that. Let's change that. So when you run the program and I run the program, we get totally different addresses. So the attacker can't predict what addresses things are at when I'm running the program. Attacker can run the code on their own system, but they'll get different addresses. So that's the idea of address space layout randomization. We're going to basically randomize the addresses, randomize where stuff is in memory. I said that memory looks like this. But what we can actually do, well, in practice, it actually looks like this. Most memory is unused. You need a little bit of memory for code, a little bit for data, a little bit for data, a little bit for stack. So a better description of how things look is more like this, with a whole lot of unused space. And the idea of address space layout randomization is take each of these segments and just kind of like jitter it up or down a little bit randomly. When the program starts, it like randomizes exactly where that's going to be placed. It's probably not going to bump up against anything else because there's so much unused space between them. So each time the program runs, these regions of memory are at a different starting point, a different location in the memory space. And when the program starts, it randomly picks where to locate each of these regions of memory by like picking a random starting address. And that means that, for instance, the heap pointers in one run will be in the left side were all very large numbers, and the right side were smaller numbers. There's a different addresses each time the program is run. So an attacker can't predict like what address things on the stack will be at, because it's different every time and random.
Why are there like blocks of like memory within each segment which are not used? Why did people
Why is there unused memory?
Yeah. Like why did people like put these unused memory between like different like portions of memory?
Well, the reason why there's unused memory, why is there unused memory between these sections?
Yeah.
The reason why there's unused memory is because most programs don't use the full address space. You can have up to 2 to the 32 addresses. Most programs use a lot less memory than that. So there's going to be unused memory somewhere. So why do we put it in between them rather than all at one side? When people originally designed the memory layout, I think they were thinking that if we leave some gaps between them, there's space for them to grow. I don't have to think very hard about how big each one needs to be. I don't know. I think it's something like that. But then when we started thinking about this for security, we thought, well, we have a lot of freedom here in how we do this. Yeah. Yeah.
Can a hacker, like, if they know the randomization protocol, would they be able to identify the new addresses?
If they know the randomization protocol, can they predict these like random addresses?
Because isn't like most randomization not actually random? It's just like
Yeah, so that comes down to how do I pick a random number on a computer? And the short answer is, if you don't have any hardware support, it's hard to do. It's hard to come up with an unpredictable random number. But most processors now have a special instruction. The CPU has a special function built into it, which is pick a random number. Exactly because it's hard to do in code. Code tends to be deterministic. So Intel has a special instruction, RD rand, read a random number. And it has some special circuitry designed to like pick a random bits for you that will be unpredictable. And they thought really hard about how to like design that circuitry using various analog effects. And so it's actually very easy for programs, if you use that special instruction, to pick random numbers, and that no one can predict. So an attacker's not going to be able to predict what random numbers my program picked when it started up and what addresses stuff is at. Yeah. Okay, so this is the idea of address space layout randomization. We shuffle all the segments of memory. And this is going to prevent a lot of exploits because the attacker needs to know the address to overwrite, or the address where their shellcode is located that they want to overwrite with to make these exploits work. If they don't know where stuff lives in memory, they're not going to know how to fill in the addresses, so they're not going to know how to prepare their input in a way that puts the right addresses in memory. That's the idea. Good thing about ASLR is it has very low slowdown. We're not actually adding any extra code or any extra overhead. It's just at startup time, we just have different set of addresses. So okay, so that's ASLR. And it's pretty good. It's pretty good, but there are ways to beat it. There are ways to beat it. The number one way to beat ASLR is through the attack you mentioned before, information disclosure. If there are two bugs in the program, one that can read memory and one that can write to memory, then you can beat ASLR. If you have one bug in the program that will like read past the end of a buffer and print it out, you can use that to print out the contents of what's on the stack. And that will print out a bunch of things on the stack like the RIPs and the SFPs and values stored in local variables, a bunch of pointers typically. And from that you can find out addresses of stuff. You can de-randomize things once you can read some pointers in memory. And then the attacker, now that the attacker knows the addresses where the stack lives, where the heap lives, the attacker can adjust their exploit and then exploit the second bug that overwrites memory to overwrite the RIP and put in the RIP the adjusted address. The plus is, from the defender's perspective, the plus is now the attacker has to find two vulnerabilities, has to find two bugs in the code. So it's harder for attackers to exploit if there's ASLR present as a defense. But it's not perfect. The other attack you could imagine attackers could do is they could just randomly brute force things. Like they brute force a canary, brute force the random addresses, just randomly guess. And it depends on the system. It's an implementation detail how much randomness there is, how much there's randomization there's done. Some early systems used only 20 bits of randomization. And so you could just barely guess. If you tried 1,000,000 times, probably once you'd guess correctly. But on the newest 64-bit machines, it's just not feasible anymore. So every mitigation that I've shown you can be defeated. They're not perfect. But some of the time they help, some of the time they increase the cost for the attacker. What people do in practice is they combine these mitigations. And a really good combination is ASLR plus non-executable pages. That combination's really good. Non-executable pages prevents the attacker from storing their own shell code somewhere in memory. There's still the ROP attack danger, but ASLR is really good at stopping ROP attacks. ROP attacks, you have to know these addresses in the code segment where the gadgets are. ASLR randomizes addresses so the attacker can't know where those gadgets will live. So non-executable pages is vulnerable to ROP attacks, but when you add in non-executable pages plus ASLR, now ROP attacks are no longer feasible. So this is like, I don't know, chocolate and peanut butter, right? It's like a great combination made in heaven. So most systems today will combine both ASLR and non-executable pages, both because they stop a lot of attacks and also because there's very little slowdown from enabling them. Can still beat the combination. It's still possible, but it takes more work. Usually it requires two vulnerabilities. One is an information disclosure to leak memory and leak the value of pointers, leak some values, some addresses in memory so that the randomization, address randomization can be, like the attacker can figure out what the addresses are at now. And then one more to like overwrite return instructions and do write a ROP chain and on the stack and do a ROP attack. So that's maybe if it costs an attacker a certain amount to go find a vulnerability in your code, that now costs them twice as much to do. So that's a meaningful improvement in security just by turning these two on. And today, most operating systems will, and most compilers, turn on these two mitigations for every program by default. And so you get some general increase in security. It is harder to exploit memory safety vulnerabilities, but still possible with enough effort. Yeah?
Is there ever a chance you'll run out of memory?
Is
Is there ever a chance like your stack frame will grow into something else?
Say more, I'm not sure I'm following.
Like you say you randomize or you put things, right? What if it grows into something?
Oh yeah, what if I randomize and then I put the stack right next to something else, and then the stack grows so much that it like goes over the edge of the other one. Usually when we do address-based randomization, we leave enough safety room that it's unlikely, and we have some measure to detect if that happens and cause the program to crash if it does. And so yeah, you got to think about this. It's a little bit, there's some details to work out. It turns out it's not that big a deal in practice, but yeah, it is. It is something you got to take care of. So bottom line is, this is general like defense against memory safety today, state of the art. If you want good defense, use a memory safe language. If you're stuck with some legacy code, enable all the mitigations you can. And for instance, like here's an example case study. All of these mitigations are widely used by Apple, and they really increase the cost of finding vulnerabilities that allow someone to like hack your iPhone and take control of your iPhone or your Mac. But sometimes these vulnerabilities still do exist, and I thought I'd show you an example of one exploit that was developed by this professional group that builds surveillance software to hack into people's machines. And they have professional security people who go look for vulnerabilities in code and write exploits for it and sell it to governments to like spy. The way they worked was they found one vulnerability in Safari, a memory safety vulnerability in some obscure Safari code that allowed executing arbitrary code. But Safari was sandboxed. It was limited in what it could do. It didn't have access to all of your files and all of your other apps and all of your data. So then they found a vulnerability in the kernel that allowed them to read addresses stored inside the kernel because the kernel was using ASLR. And then they found another vulnerability in the kernel, a buffer overrun vulnerability in the kernel that allowed them to escape the sandbox and from within the sandbox attack the kernel and now gain control of the kernel. They had to do this second vulnerability to defeat ASLR though because the kernel was using ASLR. So they in the end had to find 3 separate vulnerabilities to be able to like hack your iPhone. So they were able to be successful, but like this was a very significant operation for them to be able to put together this exploit chain. So I think it was a meaningful increase in security. All right, so bottom line is a whole bunch of mitigations against memory safety. Hopefully you're now aware of them, so you're less likely to make this mistake in your code. Hopefully you're aware of them, so you're more likely to choose memory safe languages, and you know what to do as mitigations if you can't. Let's take a break, and we'll start a new subject after the break. So a 5-minute break, and I'll put some snacks out here for anyone who wants some.